Welcome to the ninth online lecture of CS531 Memory Systems and Architecture. In the last lecture, I have explained you the basics of row hammering attack and also discuss the memory architecture that the research paper that we will discuss today. We'll start our today's lecture from the motivation of the paper that we have started discussing from last lecture. But before discussing the motivation of this paper, I need to discuss some more basics about main memory and Rohammer attack. So I'm also advising you to read this section from paper, this section 2.2, 2.3 and 2.4 by yourself. If you read these sections, you will have a clear idea about the DRAM architecture they use and how the DRAM architecture works. But from all this subsection, I will quickly discuss about this part, what is saying, the sparing DRAM rows to combat reliability challenges. Actually, when the manufacturer design a DRAM bank, they also place some spare rows. Why the spare rows? Because some of these rows may be damaged. So after designing a DRAM memory, their testing mechanism checks all these banks, and if they found that if they found any particular damaged row, then those damaged row will be replaced by the spare rows. Why this is important? Because suppose there is a row, I may have to go for this. Suppose I'm considering about row 1 here. After designing and assume that last two rows are spare rows, these two rows are spare rows. So now if this, after designing this memory during the testing phase, if we found that this row is defective and this row is damaged, so what this during the testing phase, what they will do, there is a mechanism where instead of row 1 they will use one spare row, maybe the last row, they will use last row as row 1, and this remapping will be done internally within the DRAM device, means within this device, or you can say within the DRAM bank here, or within the chip. So this internal remapping is stored in a programmable memory, one time programmable memory inside the DRAM device. So memory controller has no knowledge about it. This is the internal mapping, and this is a one time remapping done during the testing phase. So ultimately, when memory controller sends a activation for row number 1, memory controller knows that it is sending activation for row number 1, but this row number 1 is damaged, and during the testing phase, the instead of row number 1, a spare row, the last row will be used. So memory controller is sending activation to row number 1, but it is activating the last row. So this may misguide during the row hammer problem. How? Because suppose you are maintaining a counter in memory controller, and the attacker is trying to target row number 1. So what will happen? The memory controller, the counter stored in memory controller can will see that the row number 1 is targeting aggressively activating, and once this counter of row number 1 exceed the RH threshold, then memory controller has to refresh the victim rows. And which are the victim rows? Victim rows are the neighboring rows. Memory controller knows row number 1 as this row. So the neighboring row means this row number 2. Only one in this case. Row number 2 is the neighboring row. But physically, row number 1 is damaged. So victim row should be this row, not the row number 2. Right. So these type of problems is possible because of this internal remapping, and this concept is discussed here. That's why in this paper what they propose there is memory controller should not send refresh command like if this row number x is the aggressor row, memory controller should not explicitly send a refresh command for x minus 1 and x plus 1 rows. Memory controller should send a command like this, that okay, if this x is the aggressor row, then refresh the nearby rows. And when a command like this refresh by nearby rows will reach to the DRAM device, DRAM device knows that which are the nearby rows. So all these things will be you will understand when you will read this section. That's why I'm saying this section is interesting section. And You also read the section 3 for more details about the RH attack. So both section 2 and section 3 are important. They are not directly discussing about the proposal of this paper twice, but these sections are important to understand the basics of main memory and the basics of RH attack. Now let me explain you what is this module, this RCD. In previous slide I said that I will discuss it here. This RCD is an additional module used in main memory. It is called a register clock driver. So you can see one register clock driver is maintaining for each DIM. One memory controller has to manage many DIMs, and it has to send commands to all the DIMs. And if it is sending a activate command to a particular rank, then after TRCD time it has to send another command like a column read command. So maintaining all this as by a single memory controller may be sometimes very complicated, if because all this most of these DIMs are shared a common bus. So that's why these RCD, this register clock driver can store all these commands. So RCD is, you can consider as a buffer of this command which is coming from memory controller. It buffers this command, and from this RCD, the commands are issued to this DRAM devices. So why this RCD is important for this paper? Because the RH detection technique they proposed in this paper, they implemented this detection technique here in RCD, not in memory controller. So if you remember in my previous slide, I said the memory controller maintains counter, and based on this counter we detect row hammer. But in this paper, they are not maintaining these counters in memory controller. They are maintaining these counters in RCD, and there is no it is logically possible because memory controller first sends this command to the RCD, and RCD distributes this command to these DRAM devices. That's why they maintain the counters here in RCD. So now in next slide we will discuss the main motivation of this paper called twice. A disadvantage of maintaining the counters in memory controller instead of RCD is if we maintain the counters in memory controller, you can see that one memory controller is managing many DIMMs. And in a real machine, maybe there are four slots available for a channel, but we will not insert four RAM in all the slots, and assume that the first memory controller is though it has four DIMMs, but currently the only two DIMMs, in two DIMMs we have inserted the memories, another two DIMMs are empty. This may be a situation, but memory controller must have to maintain counters for all the four possible DIMMs. So this is the area overhead, or this is the overhead if we maintain counters in memory controller. But if we maintain the counters in RCD, that means these counters will be maintained internally inside the DIMM. So if we insert a DIMM in the DIMM slot, that is fine. If we are not inserting any DIMM in the DIMM slot, then we will no need to spend any cost for these counters. That's why storing counter in RCD is better than storing counter in memory controllers. So before starting the main motivation of this paper, let me explain you these terms of the terms of this table. Most of the terms is clear to you. This first term is T refresh window. It is 64 millisecond. We normally call this as refresh period or attention time. So they use the term called refresh window. So remember that these things are same. So T refw and TRET, that is T retention time and T refw is same. So this is the refresh window. This is the refresh period, means this is the 64 millisecond refresh period. During this refresh period, each row must be refreshed once. That is called periodic refresh, and you know how the auto refresh performed and what is TRFC and how it is divided into multiple parts. So these two terms is very clear to you. T refresh interval and TRFC. This is called TRFC. This is T refresh interval. I've explained it many times. TRC means read cycle time, or it's the time from one act to another act. Means activation, one activation to another activation. This time is called TRC. This is the threshold, RH threshold, THRH. Now, what is RH threshold? I have already explained. So here you can see that the RH threshold considered here is 32,768. This is the RH threshold here. And the next three parameters will be discussed in next slide. So now the main motivation is here. Performing one activation need TRC time. This is clear because see what is TRC, read cycle time or activation to activation. That means performing one activation in row is it takes TRC time. So to perform one activation command in a DRAM row, it's take TRC time, and and the refresh period is called T ref. This is the refresh window. So how many maximum number of act possible in a refresh window? Total number of acts possible per refresh period or per refresh window is this. This is the time required for one activation, and this is the refresh window. So the total number of act possible per refresh period is this. If this is the total number of activation possible in a particular refresh window, for example this is the refresh window, and in this refresh window only this number of activations are possible. This number of activations are possible. This activation may be on any rows. The total number of activation in this bank, and total number of activation in this bank in this period, in this refresh period is this. So this is limited. Now the total aggressor row per refresh period, can you count this total aggressor row? So to count total aggressor row, we can divide this with another parameter called NTH. So if we divide this parameter with NTH, then we can find out the total aggressor row. What is this NTH? NTH means this is a slight difference between this NTH and this array detector. So NTH means if you read the paper, you'll see that they have refer another paper for NTH. So NTH means the maximum number of activation to a row, which guarantees that there will be bit flip. So if suppose this is 32,000, so NTH maybe it is NTH is 139,000. So if there is 139,000 activation to a particular row, suppose row number 3. So in row number 3, in a particular refresh period, in this refresh period, if there are 139,000 of activation, then definitely there will be a bit flip. The total number of aggressor row we can count from these values. These value divided by NTH. And if this is the total number of aggressor row, then how many victim rows possible? If we consider that each aggressor row has 2 victim row, then if this is the total number of aggressor row, then how many victim rows will be possible? 2 into this, 2 into this. This is the total number of victim rows. So if we go for all these values, whatever values mentioned here, and considering NTH as 139,000, then if we go for all these values, then it has been found that only up to 20 rows can be exposed to RS attack from a bank in this duration, in a refresh interval, in a refresh window. This is refresh interval. In a refresh window, only up to 20 rows can be exposed to RS attack. I hope, and this is their main motivation. NTH says that this is the maximum number of activation to a row, after which there is a definite bit flip and possible in the victim rows and the neighboring rows. And threshold means what? So is, if you remember in one slide, I explained that when we are detecting a row hammer, if we have to detect it early. If we waste our time and if we detect it too late, means that means that when we are detecting that there is a this is the aggressor row, before death detection, if it has already flipped the victim rows, then there is no point of that detection. So that means we must detect it early. That's why this detection threshold, what I said earlier, is actually a threshold detection threshold. So this detection threshold must be less compared to the actual threshold. If this is the actual threshold, then the detection threshold must be less. That's why if it is 139,000, then in this paper they consider the detection threshold as 32,768. The value they have considered here is a mathematically correct value. I am not explaining it today that how they have come up with this value, but in next class I will explain how this value is considered here. If the total number of aggressor row is limited within a refresh window, and the total number of victim rows is also limited, then this is the main motivation of this paper, that if only a limited number of rows can be attacked or can be activated within a refresh window, then we no need a huge amount of counters to maintain all this activation counter. only a limited number of counter is enough, because you can see that in any refresh window, there is a limit that how many unique rows can be activated. Since the total number of activation is limited within any refresh window, then only a limited amount of counter will be enough to detect the row hammer attacks. This is the main motivation of this paper. So the twice guarantees protection against RH attack with minimum number of counters. So how they are maintaining all the rows with limited number of counters? They remove the entry of a row from this counter if the row is not frequently accessed or frequently activating during a particular period, and that period is called PI here. So this is their main concept, because if the counters are limited, they cannot they maintain a counter for each row in the bank. So what they're storing they are only counting the number of activation in the most recently accessed rows and they are using another interval. That interval is called PI. So during this PI interval, if a particular row is not accessed, then they are removing it from the table or from the counter. So and to maintain the counter, they are using a table like this. This is the table for, or you can say this is the complete logic of twice, or and this concept, there is there some logic circuit is also required. So some adder, shifter, and comparator is required to implement this the concept of this paper. And with this they need this table, or you can say this is the counter. They are storing the counter in a table. Each entry or row in this table is correspond to a particular DRAM row. If the valid bit of any entry in this table is 0, means that entry is empty. This is the row address. This where they are storing the row address of the DRAM rows. This is the actual counter. The counter that we are saying, that how many number of activation performed in this particular refresh window, that is stored here in this column, activation counter. And this is life. This life means this PI interval. This PI, that means once this particular row is in counter from how many PI intervals. So and this is called live here. So if you see this entry, this is a valid entry in the table, and this is the row address. And up to until now, this particular row is activated 23 times in a particular refresh window. Remember, whatever I am saying here is only for one refresh window. This is the refresh window. That means this PI interval is a very small interval. Normally this PI is same as T refresh interval. So there will be multiple PI within a single refresh window. So whatever I'm saying here is for one particular refresh window. Once a new refresh window will come, everything will be restarted again. So now here within a particular refresh window, this row is activated 23 times. Yeah, 23 times. And the live value 6 means this particular row is in the table from last 6 PI interval. If you say go for this particular row, then this is also a valid row, and this is the row address. So this row has activated twice during the this refresh period, and it is in this table from last one PI interval. So this is called life. So I hope all this column and elements are clear. What is valid, what is row address, very straightforward. ACT count, activation count, this is also straightforward. Life, what is life? I already explained. Life means means if life value is 6, that means this particular entry is in this table from last 6 PI intervals. And PI interval is in this paper they consider same as this refresh interval. The number of activation to a particular row within a refresh window must exceed this value, TRH value. Then only we can say that this is the aggressor row. That's why this is our detection count, detection threshold, right? So we can only say a particular row, suppose row number 3 in in a bank is aggressor row. We can only say that row number 3 is aggressor row if within a particular refresh window the total number of activation to this row is more than this value, THRH value. So if there is if there is any possibility of RH attack, then a particular row must be refreshed this number of times within this refresh window. This refresh window is divided into multiple PIs that I've already explained here. So if this refresh window is divided into multiple PIs, then on average in a particular PI, how many activation is required for aggressive row? So remember, this line and next line is related. Here I am saying the TRH number of activation is required for a particular row during this interval for a RH attack or for a aggressor row. Now, if TRH amount of activation is required during this interval, this refresh window, and now this refresh window is divided into multiple PIs, then what is the average number of activation required in each PI for aggressor row? That is this. This is the average number of activation in each PI which is required. So if you understand this point, then you'll also understand this. So if you see these point, these they have considered as 4, and this is called THPI. This is the threshold of each PI. So in during any of this life, this is called the PI is called life. Now, so during any of this PI interval, if the total activation is less than 4, then definitely there is no chance that this row, no chance that this row will become a aggressor row in this and this refresh window. And if the total activation in a PI interval is more than THPI, then there is a chance of RH attack in this row in future within this refresh window. So how twice works? So first twice receives a DRAM command, or you can say twice receives a activate command. So once the twice receives a activate command, it enters the corresponding values in this table. And how it will enter, then first to enter a new entry in this table must have a free location. Here you can see there is a value 0 invalid bit, that means this row is free, so you can easily enter a new entry here. So every time a new activation command comes to twice, it will enter a new entry here, and the activation count will set as 1. And if there is activation command comes for the existing rows in this table, then only these activation values will be incremented. So this part is clear, I think. And during this activation is anytime if this counter value exceed TRH, this is TRH. So at any time if these counter values exist TRH, that means this is there is a detect we have detected a RH attack. This is the detection. So the moment we detect a RH attack, you know what is the mitigation technique. We have to refresh the neighboring rows or the victim rows. So that is written here. If ACT activation count reach this RH detection threshold, then twice refreshes the adjacent rows of the entry and deallocates the entry. After refreshing the victim rows, it will deallocate the entry. Deallocation only means changing this bit from 1 to 0. That's it. That is the deallocation here. Now the next question is when they are calculating these values, these 6 or 7, how they are calculating these. To calculate these values, they are not calculating every time. And this is also one of the reasons that when they consider PI as equal to refresh interval. So why? Because if you remember from last class, what I said, that after every refresh interval there is a refresh command issued to this bank, and this refresh command, when after issuing a refresh command, it is taking TRFC time to complete the refresh operations. And during this TRFC time, the bank is blocked for normal read write operation. So they are utilizing this blockage time, because since at this time there is no normal operation possible in this bank. So when this bank is refreshing the rows, at the same time they will do some work in this table. So the whatever they are doing in this table is not comes to the critical path. That's why when the bank is busy in doing all this refresh, they can do some of work here. That's why the PI is same as T refresh interval. If the total number of the average number of activation per PI must be 4. If the average number of activation per PI is less than 4, then there is no chance that this row becomes aggressor row. So what they are checking is that every time if for example here, this is the total number of activation, this is 23, and this is the life of 6, and per life there should be 4 activation for aggressor. So they will multiply these two values. See, they'll multiply these two values. 4 into this, 4 into this. This is the threshold pi. So they'll multiply 4 with this, 6 into 4. If 6 into 4, that is 24. So if this count is less than 6 into 4, that means there is no chance that this row will become an aggressor row. So they can remove this row from this table. That means they'll convert this to 0. And that's why I said in last slide that this point is important. This THPI is important. Should I repeat it again? I'm repeating it last time that what is THPI? THPI means in each PI interval, these are the PI intervals. So there are many multiple PIs interval possible in a refresh window. This is a refresh window and these are the PI intervals. So in each PI interval, average number of activation must be 4. If it is less than 4, then there is no chance of row M at in that particular row. Otherwise, what we will do, if suppose this value is 27 and 6 into 4 is 24, so this value is higher, so that means that there is a chance that this row becomes the aggressor row, but it is not a aggressor row right now, because to become a aggressor row, these count must be this THRH 32768. It must be this or higher than this, then only we can say this is aggressor row. But if current value of this is 27, then this value is more than 6 into 4, that is 24. So there is a chance that this row will become aggressor row, so we'll keep this row and we'll change this value from 6 to 7, because now one more pi interval is completed, so we'll change this from 6 to 7. So the complete operations of this paper is already explained. Whatever I've explained covers all the operations of this paper. So mainly they are managing the RH detection with less number of counters because of removing the unnecessary entries from this table. This is the main concept. And what should be the actual size of this table will be discussed in next class. Now this is the example of whatever I explained in last slide. So suppose this is the table content. If you see in this table content, this is the current picture of this table. So there is two valid entry and this is not valid entry because there is a 0 stored here. At this moment, if this twice table receives a command, activation command, and for this address 0xf0. So 0xf0 is not in this table. So what we will do here, we'll enter 0xf0 here because this is a free entry, because this is a valid bit is 0. So it will perform here. See, so this 0xf0 is entered here. Now it is, and the counter is 1 and the life is 1. This is the first life. At this moment, if another activation command comes, and this activation command is for this address C0. So now see, C0 is already in this table. So what we have to do here, we'll just need to change this counter value from 7 to 8. See, it is 7 to 8. And now there is another activation request came for 50, for row number 50. Row number 50 is also in this list, in this table, sorry, in this table. So now we have to increment this counter. So if we increment this counter, this value will be 32768, which is equivalent to THRH. The moment we'll increment it to THRH, what we have to do, we have to go for refreshing the nearby the victim rows, or refreshing the adjacent rows. Then we have to refresh the adjacent row. If you remember the operation I have explained in previous slide, that once you refresh the victim rows, you can remove the entry from the table. So they have removed the entry. How they remove the entry? Just changing it to 0. So the entry is removed. Now there is a auto refresh command here. This auto refresh command means it reached a interval, means one pi interval is done, and now means after this auto refresh command is, that means there is a refresh command we have to issue now. This means that this refresh interval time has been spent, and now a memory controller issued a refresh command, and it will take TRFC time to perform the refresh. That is called auto refresh. So at the same time, when the bank is performing auto refresh, we do some task in table also, that I've explained in last slide. What are the tasks here? The task here is, we will check all this here. So the check this value is 8, and how many life it has performed, 2, and the threshold pi is 4. So 4 into 2 is 8. So it is, and the current value is it is not less. So that means there is a chance that this row may become a aggressor row in future. So what we'll do here, we will not remove this row, we'll keep this row in the table, but we'll change this value from 2 to 3. This is done from the first row. And what we'll do in the second row, well, second row will check that in the next this total count is 1. So if we multiply 1 with 4, then this is 4. So 1 is less than 4. So it means that this row has no chance to become a aggressor row in future. So we'll remove this row from the table. So this is the scenario here. This row is became 3, the life has become 3, and we have removed this row. So all this operation of twice is explained. How it is detecting, you can see it is detecting here in this particular scene. In this particular case, if a activation command comes for row number 50, then row number 50 in this particular refresh window already performed this 32,767 activations. So if one more activations came, then total activation reached this threshold. So that means this has become aggressor row, or that means we have detected a aggressor row. So we have to refresh the victim rows, and the moment we refresh the victim row, this will remove the entry of aggressor row from here, because it is not required, because the whatever damage possible by this aggressor row is already mitigated or already handled. So we'll remove this entry from here. You can see the change in this table. This is the one part. Second part is how we are incrementing every time. So if this is the current table, if a request came for a new row, then we'll add a new row here. If a request activation request came for a existing row, I'll simply change the activation command here, and increment the activation counter here. And another last part is what we have to do during the auto refresh part. That means after ending of each pi interval. There are many pi intervals possible in a refresh window. Total number of pi interval is, I think, this total number of pi interval is this, it is written here. And in this paper they say pi interval is same as refresh interval. So after every refresh interval, a pi interval is also ending. And after every refresh interval, what the bank is doing a refresh command, executing a refresh command. So it will take trfc time. So trfc time the bank is blocked. So in this paper they are using that these trfc time when the bank is blocked to do some additional do some processing in this table. And that process, that's why this processing is performed when auto refresh is performing in the bank. And the operation performs during this time is already explained. How they are doing it with limited number of counters, you can understand if you can understand this example properly, because they are not they are maintaining counters only for the recently accessed rows. If a row is not recently accessed more than these thpi values, then there is no chance that this row will become aggressor row in future in this particular refresh window. So they are removing the entry for that row from this table, and this table is the counter table. So now the next question is what should be the size of the table? Because if in this situation, suppose in this situation, first case, when a new request came, there must be an entry in this table. If there is there is no free space available in this table to enter a new row, then there is a issue. So that conflict should not happen. So what should be the maximum, or so what should be the size of this table, size that this type of conflict should not happen? The and where to place this mechanism, why? So yeah, and at the beginning of today's lecture I said the concept of this twice is stored in rcd and not in memory controller. So why they have stored in RCD, not in memory controller? What should be the size of the of this table, and what how this technique is guaranteed to detect a RH attack with 100% accuracy. So all these things will be discussed in next class. Next lecture will be uploaded by Sunday morning. So before Sunday morning, please read the paper and try to understand the concept. After today's lecture, it will be very easy for you to understand the paper. So read this paper, understand it. Thank you for stopping here today.